Hi everyone. So this is the third lesson, last of gravitational fields. It has to do with the gravitational potential and gravitational potential energy. As we will see, there are different definitions. So we will look at gravitational potential at the point, the definition of it, and we will look at the gravitational potential is zero at infinity, which I will explain. It's based on basically work done to separate masses that are attracting each other. Then we have the equation for gravitational potential that we'll look at. We will also look at the force distance graph for a point or spherical mass, the gravitational potential energy and how to calculate it, and what we mean by escape velocity. So to start with, what is gravitational potential? So gravitational potential at the point in a gravitational field is defined as the work done per unit mass to move an object to that point from infinity. So if we look at the actual definition, which we just did, it will be Vg is the work done per unit mass to move that object from a point to that point, from infinity. So if I had, let's say this is the big mass, let's say the Earth, and I had another mass at infinity, let's say that's infinity all the way here, then it will be the energy required per unit mass to move that object to a point here, let's say, from infinity, if this was infinity. So you need to know that part very well. From infinity, you won't get marks if you don't mention that. What should be the units? Well, if we look again at the equation, the definition, the units will be joules, so work done is in joules, and per unit mass is in kilograms, so it will be joules per kilogram. Is this a vector or a scalar quantity? Well, it's a scalar quantity because we're talking about energy and mass, which are both scalar quantities. They don't have a direction. What do we mean by infinity? Well, when we talk about infinity, we actually mean that the gravitational potential will be zero at infinity. So we know that the gravitational force is attractive, so work needs to be done on the body when we move it in the opposite direction. So we're moving it away from the surface of an object M with a mass M, So if I want to move an object that's on the surface of a planet, for example, towards infinity, I will need to work on the body to bring it to any point in the gravitational field of mass M. So it will be a negative value. So if this is infinity and gravitational potential is zero at infinity, that means that every other part around the mass will have a negative Vg value. So, a gravitational potential value, since it's attracted to the mass. So I always need to provide the energy, which will be negative amount of energy. So sometimes it's easy to draw a diagram to help you remember the definition. With me, it's simply got to do with a mass and how an object should be moved from infinity to that point, and is the energy or work done per unit mass. So a diagram here shows, so ignore this bit. So in this diagram, we have a big mass, a body of mass, and let's say I have a 1 kilogram object at infinity. At infinity, the gravitational potential is maximum, which is zero. That's because it takes energy, so external work must be done to move objects apart from M. So infinity will be the maximum value, so everything else will be negative since gravitational force is attractive, and any other value in between will be negative in terms of potential, gravitational potential. So how can we calculate the gravitational potential at the point in the field? It will be minus gm over r, where Vg stands for the gravitational potential. G stands for the gravitational constant. M stands for the mass that causes the of the point mass, sorry. M stands for the mass of the point mass. But this point mass will be the one that causes the field. And r is the distance from the point mass to producing the gravitational field to that point. So is the if we look at the units, that will be kilograms, meters, and joules per kilogram. So if I were to draw a graph of Vg, so for gravitational potential against r, since it's a negative value, it is a negative value. Did I show that there? Yeah. So it's a negative value because it's going to be negative until it's maximum at 0 at infinity. So I will get a graph that looks like this, especially if this is for the Earth. This is where the radius of the Earth will be. So at the surface of the Earth is going to be the maximum magnitude of potential, because it's the smallest distance I can actually take from the center of the Earth. And then if I want to get a straight line graph, then I will need to plot Vg versus 1 over r, since gravitational potential is minus gm over r. If I rewrite this as, let me actually rewrite it in a different way. So minus gm times 1 over r. I will compare that to y is equal to mx plus c. Now that means my y will be the Vg, my x will be 1 over r. There is no y-intercept since there's no plus or minus anything, so that will be 0. So that leaves my gradient to be minus gm. So if I wanted to plot it as a straight line without taking into account the negative value, it will be a straight line going through the origin with a gradient that's equal to gm. So if I wanted to calculate the mass of a point mass or a planet causing a specific gravitational potential at a specific distance, I could get the gradient, and then I would divide the gradient by gravitational constant to get the mass. Okay, so there's a few more things about gravitational potential. There's always changes in gravitational potential too. So if I moved from one point in the gravitational field to another point, this will result in a change in gravitational potential, which we show using delta Vg, which means change in gravitational potential. So if we're moving towards a point mass or a planet, that will result in a decrease of gravitational potential. So we're moving towards the mass, there will be a so like you see here, changes can be negative, so moving towards the point mass will result in a decrease in the gravitational potential, but moving away from the point mass towards infinity results in an increase in gravitational potential. So it will be a positive change in thing. So this will be this will be negative, but moving away from it, the change will be positive. We will do some exam questions in class to show you the application of this concept. But now, for now, we'll move on to quickly the other points. So we have spoken about the gravitational potential at the point as the work done per unit mass in bringing that mass from infinity to that point. We also stated that gravitational potential is zero at infinity due to the fact that you have to work to remove it. So all of the other values are are negative until we reach infinity, which is zero. We saw the equation. And we will talk about the next 3 points now. Okay, so for gravitational potential energy, we define it as the work done to move an object of mass m from infinity to a point in a gravitational field. So it's usually given by this equation. So the gravitational potential energy, that's the mass of the object we're moving. And this is the gravitational potential. Since we usually need to determine changes in gravitational potential energy, we can rewrite this equation as the change in gravitational potential energy is equal to the mass of the object times the change in the gravitational potential. Now, if we talk about, before I move on, I want to just mention briefly gravitational potential energy in a uniform gravitational field. So basically at the surface of the Earth. So we're at the surface of the Earth. We know that the gravitational potential energy changes with height. And we usually calculate it using mgh or mg delta h. But when it comes to gravitational potential energy in a radial field, so where the field is not the same, we already know that Vg is equal to minus Gm over R. So if I substitute this equation into this one, I will end up with E is equal to M minus Gm over R. So simplifying it will give me minus Gm M over R. Now, a very common mistake is that people in exams always confuse gravitational potential energy with gravitational potential. So be very, very careful when you are picking the equation that you really know which one you keep picking up, because they don't give you the words of what each symbol stands for, but they do give you the symbols. So I'll give you a drawing example. So if you're moving from A to B, for example, then you will have two different gravitational potentials. Since the gravitational potential changes, that means the gravitational potential also changes. And in this case, we know that the gravitational potential energy will be transferred to the kinetic energy of an object in order for it to accelerate to that point. So it's still energy, don't forget that. It's just acting in a radial field in a bigger space than, just the surface of the Earth. So from Newton's law of gravitation, we saw that force is minus Gmm over R squared. If I draw the graph, it will look like this graph. And we also know that if work done is equal to force times distance, then I can get the area under the graph. So force times distance is always the area. If I multiply values, I have to get the area that's covered by the graph that's shown here. Okay, so the last thing that we'll look at is escape velocity. So for an object to escape the gravitational field of a planet, it needs to be supplied with energy that's equal to the gain in the gravitational potential energy. So it needs to be supplied with energy. Oh, picked the wrong color. Supplied with energy that's equal to the gain in GP needed to lift it out of that field. So we will consider the energies that are taking place. So which energy stores are involved in an object being put into orbit, and how we can calculate that minimum speed for it to be put into the orbit. So in order to put an object in, to fire an object upwards, to get it out of a gravitational field, and if we ignore air resistance, so let me just note that down. We ignore any air resistance, so by ignoring air resistance, we're ignoring any losses of energy as heat or thermal energy stores. So the kinetic energy of an object that's projected into the gravitational field will be equal to the gravitational potential energy at that point in the field. So in other words, we will have kinetic energy, which is a half mv squared, which is equal to the gravitational potential energy, which is minus gmm, but I will ignore the minus sign because we're only interested in the magnitude of it, gmm over r. And for this to be able to be met, the minimum velocity will be the escape velocity, basically. So that will be, if we simplify it, the mass of the object doesn't matter. It will be v squared is equal to 2gm over r. So that will be v is equal to square root of 2gm over r. So this is the escape velocity. G is the gravitational constant. This is the mass of the object causing the mass of the object of whose field, gravitational field, we're trying to escape, and r is the distance from the center of that object. So yeah, the escape velocity on any planet will be the same for any object regardless of what mass they have, because the mass is not included, it cancels out. Please do not confuse this with the other proofs that we have seen for this topic. So we have seen, I forgot even now what we have proven. Oh yeah, we have shown the speed of an object, of a satellite being put in orbit. That has to do with forces. When we are talking about escape velocity, remember to deal with it in terms of energy transfers. So kinetic to GPE in terms of radial field. We will do practice questions in class. I'll just try to keep the video short. And if you have any questions, which you might do on this part of the topic, please let me know in class.